Hello and welcome to this lecture on fundamentals of electric drives. In the last lecture, we were discussing about the slip power recovery scheme, and in fact, we were discussing about one type of drive which is called a static Kramer drive. The static Kramer drive looks like this. So, we have a rectifier in the rotor circuit, then we are recovering this power P r and feeding this power back to the supply. Now, in this case what we have here is that as we observe in this case the slip can be controlled by controlling the triggering angle alpha of the converter. So, we will also try to derive some of the relationship. Now, neglecting losses, in fact, what we can say here is that a rotor loss, neglecting losses in this case, losses in the circuit, this resistance, this inductance we have assumed to be an ideal inductor. So, the resistance we can assume to be equal to 0. So, neglecting losses, we can say that the slip power which is recovered, which is the power, that is this is the slip power S into P g. The slip power which is being recovered from this is equal to V d 1 into I d, same as V d 2 into I d. So, the power which is being recovered is S into P g is equal to P r. So, P r is S into P g, that is equal to V d 1 into I d, and it is same as V d 2 into I d, the same power is being recovered here. So, what is the mechanical output? The mechanical output is 1 minus S into the air gap power, and that is equal to the mechanical output. In fact, the output which is coming out of this as P m is having a torque T and omega m is the speed. So, the torque of the motor is T and the speed is omega m. So, we can say in this case that is equal to torque into omega m, and that is equal to torque into omega m s is the synchronous speed into 1 minus s. Or from this equation we can say that the torque is equal to P g divided by omega m s. So, what is P g? P g can be obtained from, let us say this is our equation 1 and this is our equation 2, let us say, and what we obtain here is equation 3. So, P g can be obtained from equation 1, can be substituted in equation 2. So, this will give us torque is equal to P g is equal to V d 1 into I d divided by S by omega m s. So, this is what we have here, and what is V d 1? V d 1 we have already calculated, we have already found out the value of V d 1, which is from this equation 3 root 6 V s by pi n, that will substitute here. So, this is 3 root 6 V into S by pi n I d by omega m s by S here. So, in this case S and S will cancel. So, that is equal to 3 into root 6 V I d by pi n. Now, if we see this equation, the equation for the torque is given as a function and it is proportional to I d. So, we see that the torque is proportional to I d. V is constant, 3 into root 6 is also a constant, pi and n are the constant quantity. So, T is proportional to I d. So, what we get here T is proportional to I d. So, if we want to control the torque of the induction motor, and hence if you want to control the speed of the induction motor, we have to control the DC link current. I d is the DC link current. So, the DC link current is I d. So, if we can control this current I d, we can control the torque of the motor, also the speed of the motor. So, that is what is coming from this equation. Now, let us draw the AC equivalent circuit of a static Kramer drive. Now, we draw the AC equivalent circuit from the rotor side. So, the AC equivalent circuit will look like this. So, we start from the rotor side here. So, this is VR, the rotor applied voltage in this case. We have the rotor resistance and we have the rotor leakage reactance, which is XR. The frequency here is the slip frequency SF. So, we have to multiply with S. Now, we are referring everything from the rotor side. So, the stator reactance is referred as XS prime from the rotor side, the slip resistance the slip frequency. So, we multiply here with S. Then we have the stator resistance referred from the rotor side R r prime. So, this is what we get here. So, this is the applied voltage. So, the voltage here is S V referred from the rotor side. So, S V prime, and this is the rotor resistance R r. So, this is the AC equivalent circuit of the motor, AC equivalent circuit from the rotor side. So, what is R s prime? R s prime is R s divided by n square, n is the stator to rotor turns ratio. What is X s prime? X s prime is X s by n square. So, n is the stator to rotor turns ratio, stator to rotor turns ratio. So, we are referring everything from the rotor side, and this equivalent circuit will help us to find out the current, the equivalent current in the circuit. Now, let us draw the phasor diagram. So, the phasor diagram of the drive is as follows. We start with the phase voltage, that is V, and the phase voltage supplies a magnetization current which is I m, which is almost pi by 2 lagging behind this, or say for example, if there is some loss component, that will have some loss component here. So, this is I m, and over this we have the rotor current which is I r referred from the stator side, and then when we join these two we get the overall current. Now, this diagram we are drawing, this is our stator current which is I s, and the rotor current here is I r, and then we have also a magnetizing current. We also have a transformer current which is being taken from this side. So, the transformer current which is taken by the transformer is the current which is I t. So, transformer current is basically drawn by the converter. So, the converter is drawing the transformer current here. So, the converter is drawing the current, and we have a delay angle which is alpha, alpha is larger than 90 degree. So, in this case if we see here, we draw the transformer current, and this is the angle alpha. So, alpha here is 90 degree, and alpha maximum we said it is something like 165 degree. Alpha maximum is equal to 165 degree. So, if we assume that the transformer current is constant, the locus of the transformer current is a circle. Locus of the transformer current is a circle. So, this varies in a circular fashion, but the range of the alpha is from 90 to 165. So, the transformer current will have this phase, this value when alpha is 90. So, if alpha is 90, what is the slip? Now, if we see this equation, if alpha is 90, what is the slip? If alpha is 90 degree, what is the slip here? Slip is minus n by m into cos 90 degree, that is equal to 0. It means, when we exactly put alpha equal to 90, the converter is not recovering any power. So, the slip equal to 0, it means the rotor is rotating at synchronous speed. When alpha is alpha maximum, alpha is 165, which is alpha maximum. What is the slip here? Slip is minus n by m into cos of 165, which is a negative value, which is greater than 0, which is equal to S maximum. So, when alpha equal to 0, the slip equal to 0 here. When alpha is 165, the slip is S maximum. So, S maximum means this is the lowest possible speed, lowest possible speed. When the slip is higher, the speed is lower, because we have the equation, the speed is equal to omega ms into 1 minus s. When s equal to 0, the speed is the synchronous speed. When s is S maximum, the speed is minimum. So, in this case we get the minimum speed. So, what about the combined current? So, this is IT, the transformer current, which is drawn by the transformer, and this is the transformer current corresponding to 165. So, if we draw the final phasor of the current, that will look like this. This is the total current. I total. So, what is this I total? I total is a current which is flowing or being obtained from the grid. So, we have a grid here, the current which is obtained from the grid is I s plus I t. So, I total is equal to I s, the current drawn by the stator of the induction motor, plus the transformer I t. So, this I total is having this value. And what about the power factor here? The power factor angle in this case is theta. The angle that this makes with the voltage V is called the power factor angle. So, when we operate at lowest possible speed, what is the power factor angle? So, we can draw it corresponding to this. So, this is for maximum possible slip or the minimum possible speed. So, we get the value of the total current, which is this. So, this is I total for maximum slip. And what about the corresponding angle here? Angle is theta. So, what we find here is that when we change the speed, the power factor also changes, and in fact, when the slip increases, the power factors become poorer and poorer. So, we conclude here that at a lower speed, the motor operates at a reduced power factor. So, at lower speed, the overall power factor of the drive is less. So, at lower speed the overall power factor of the drive is less. So, it means when we decrease the speed decreases, the power factor also decreases. So, this is a very important conclusion. As the speed decreases, the power factor also decreases. So, we have to remember this, that at reduced speed the motor runs at a reduced power factor. The overall drive, static Kramer drive, runs at a reduced power factor. Let us now draw a closed loop speed control scheme for the static Kramer drive. Closed loop speed control scheme for static Kramer drive. Now, here the speed is less than the synchronous speed. So, we have the AC line here, it is a 3-phase line, and our motor is a 3-phase motor. This is the slip ring motor. So, it is a 3-phase stator and 3-phase rotor, and in the rotor side we have a converter, a rectifier here, uncontrolled rectifier in the rotor side, and then we have a converter to recover the power. This is a fully controlled converter bridge. So, we have the DC link here, this is ID, the DC link current, and this is the inductor, that is LD, and we have a transformer which is connected to the 3-phase converter and is feeding the power to the grid, thus it is recovering the slip power. So, this is the AC supply, three-phase, and this is the slip ring induction motor, slip ring induction motor. So, we sense the rotor speed by means of a speed sensor. So, here we have a speed sensor, and the speed sensor gives us the feedback value of the speed. This is omega m, and we have here the reference speed, which is omega m star. Then we feed this to a PI controller, PI 1. So, this is the speed error, and then this is followed by current limiter, here we have a speed controller, and this gives us the reference value of the current ID star, and this is the feedback value of the current. We have a current sensor here, by means of which we can sense the actual DC current, and this is fed to a PI controller. And then we have the firing circuit. So, which gives an angle alpha, the triggering angle to the converter here, and this is the closed loop scheme of the drive system. So, in the closed loop, what we are trying to do? We are trying to control the speed of the slip ring induction motor below the synchronous speed. So, we have a reference speed here. The reference speed is omega m star, and this is compared with the actual speed from a speed sensor, and the speed error is fed to a PI controller, that is a speed controller, and then we have a current limiter which gives us the reference value of the DC link current. The DC link current reference value is compared with the actual DC link current, and then the error is generated. Error is a current error that is fed to a PI controller, and this is the current controller. This is the current controller, and this is feeding the firing circuit of the converter, and the converter operates within this range alpha greater than 90, less or equal to 165, that is the alpha maximum, and this operates in the inverting mode. So, the power, the slip power is recovered from the rotor side, and if we assume that the DC link is lossless, the same slip power is fed to the grid side. So, this is the static Kramer drive in closed loop. So, by controlling angle alpha of the converter, we can control the speed. Since this is in the closed loop, we have to just change the reference speed. By changing the reference speed, the speed can be controlled. So, now this is about the slip ring induction motor control. Now, we will now see the motor control, that is the synchronous motor control. How do we control a synchronous motor? So, we will be next discussing on synchronous motor. Synchronous motor are of two types. They are divided into two distinct type. One is called a wound rotor or wound field synchronous motor, and the second type of synchronous motor are called permanent magnet synchronous motor. Synchronous motors are primarily not very commonly found, especially the wound field synchronous motors are used for very high power application. High power means in the megawatt range. So, the wound field synchronous motors are applied for very high power application, high power application. So, high power applications means especially in the megawatt range, whereas the permanent magnet synchronous motors are used for low and medium power application, medium power application. Which means in the few kilowatt ranges. Now, in case of wound field synchronous motor, we have two types of rotor. One is called a cylindrical rotor type, other is called a salient pole rotor type synchronous motor. So, let us see a cylindrical rotor type wound field synchronous motor, cylindrical rotor. So, in this case the rotor is like a cylinder. So, we have the conductors placed here in the rotor, and one set of conductors are carrying dot current, other type of conductors are carrying cross current. So, the net field is in this direction. So, this is a cylindrical rotor, and the second type of rotor is called a salient pole rotor. So, we have the rotor which is a salient pole structure, the poles are protruding out and the windings are placed like this. This is carrying a DC current. So, we have IF here, and the flux is produced as before. Here the flux is somewhere like this and the flux is produced like this. So, in a salient pole rotor, the rotor air gap is non-uniform. So, in this case the air gap is non-uniform. On the other hand, in cylindrical rotor air gap is uniform. So, we can say that air gap is uniform here, air gap is uniform, and in this case air gap is non-uniform, air gap is non-uniform. So, if we see a permanent magnet synchronous motor which is also called PMSM motor, permanent magnet synchronous motor, this can be divided into two types. One is called a surface mount permanent magnet motor, surface mount permanent magnet synchronous motor PMSM, and this consists of again two types. One is called a projecting type, and the second one is called inset type. In permanent magnet synchronous motor, the rotor is a permanent magnet, the field windings are absent. So, we produce the rotor flux by having permanent magnet. In projecting pole type permanent magnet rotor, we have the projecting magnets in the rotor. So, in the rotor we have the projecting magnets. So, this is the rotor structure and we have the magnets here. So, this is the magnet. Similarly, we have magnet here and we have the magnet in the rotor, and this is rotor in the magnet. And in inset type of rotor, we have the rotor, the magnet is inside the rotor aligned with the surface. So, we have the magnet which is of this sort. So, we have north pole, south pole, north pole, south pole. Similarly, we have north pole here, south pole here, north pole here and south pole here. So, broadly we have seen that we have two types of synchronous motors, wound field synchronous motors, and we have permanent magnet synchronous motors. Wound field synchronous motors are applied for higher power application in the megawatt range, and permanent magnet synchronous motors are used for low and medium power application. So, we will be discussing the control of synchronous motor in the next lecture. So, we conclude for this lecture today and will continue with synchronous motors in the next lecture.